All right, so we are now ready to tackle stage 3 of the TP camera system's primary functionality.
Right. This is where we're going to calculate our desired position.
That's right. Stage 3. And this, again, yeah, this is all about desired position. In fact, I guess I should write out the name of the method. This is calculate desired position. Now, what is the basic goal of calculate desired position?
Well, we need to figure out where our camera is going. To figure that out, we have to take the information that we gathered from handle player input, which is our mouse X, our mouse Y, and our desired distance.
Right. We already have our desired distance. In fact, I'm going to make a special note of that. We have desired distance at this point.
Yep. We also have mouse X and mouse Y, which is our rotations in X and our rotations in Y.
We have mouse X and we have mouse Y.
Which is everything we need to calculate a position.
That's right.
Normally, if we wanted to know exactly where it was going to be. But there's a problem with that.
Well, the problem becomes it's all from the word desired. Why do we have desired? Why aren't we just moving this to some absolute location? And it really all boils down to one word. It's the whole reason we're here, and that is smoothing. Smoothing is its own set of complications, if you will. Instead of just telling the camera exactly where we want it to be and how far away we want it to be, we instead want that value to smoothly transition over time. And smoothing is a fairly simple thing. It's a fairly simple concept to graph out. We just need to be aware of it, aware of the ingredients we need to make it happen, and the order in which we need to solve our math in order to get it all to work properly. So first off, let's just take a look at the very basic concept of smoothing and the ingredients you need to make it happen. So smoothing is something you can graph out. Like anything, it's just a type of motion. And if we were to create a graph that was distance over time, all you need is a start position and an end position. And really, if in the place of the word end position, we can say desired position, because that's exactly what it is. And a smooth calculation is going to do the following. It's just going to create a curve that eases in and eases out, just forms a nice S-curve that flows between these points. That's it. Now, there are some particular factors that control this curve, and we're going to talk about some of the inherent Unity functionality we can use to do that here in just a few minutes. All you need to know at this point is that that's why we have our desired position, because we already have the current location of our objects, be it for distance or for their orbital position. We need that desired position so that we can perform some kind of smoothing. Okay? Now, again, we already have our desired distance. We have our current distance. This means we have all of the information that we need to smooth out our distance first, which is good because there is a specific order that we have to do everything.
Right.
First off, we need to solve our distance. Distance has to be finalized before we try to figure out our orbital position.
Right, because if you remember a little bit ago, we mentioned to calculate a position in the context that we're doing it, which is a rotation X, rotation Y, offset by a distance. We have to know the distance before we can calculate the position.
That's right. So we're going to solve our distance, and then we're going to use that result. So use distance to solve desired position. Now here's the thing. We're not going to really do anything about the actual position of the camera here. That's going to be handled in an entirely separate method. We're going to be handling the motion for that inside of update position later on. All we're going to do, as the name suggests, is just calculate where that desired position is going to be. So here's how this has to work. What do I mean when I say solve distance? Well, that's where it kind of gets funny, because we're not just smoothing position. We're smoothing two things. We are smoothing our distance, or smoothing the distance transition, I guess.
Right. So when the camera is changing its position, or not so much its position, but its distance from our character, we're smoothing that transition from where the camera is to where we want the camera to be.
That's right. And just to make sure everybody's on the same page, when we say smoothing distance versus smoothing position, position refers to our location along the orbital ring. So when we say the word position, that's what I want you to think. Distance is how far. It's kind of like a radius from the center of the character out to the orbital ring,
or basically how big our orbital ring is.
That's right.
If our distance is at our min, we've got our smallest orbital ring that we can have. If our distance is at the max limit, we have the largest orbital ring that we can have.
That's right. In fact, just to help people out, because you know I like pictures. This is position out here, and this is distance. So when we say that, that's what we're talking about, with, of course, this being the location of the look-at target, or the target look-at, whichever way you want to look at it. Okay, so now we've got the kind of the order in which we need to perform all of these things. Now, fortunately for us, I mentioned earlier, solving smoothing requires two key elements. We need to know where we are. We need to know where we want to be. And really, that's it. There's some other, well, we also need to know how much time we want to take to get from point A to point B, but we'll talk about that in just a moment. But we already have our desired distance. That came to us from the handle player input method. We have our current distance. So now we can go ahead and do a smoothing operation on the distance of our camera, so that if we rolled the mouse wheel back, we get a nice smooth transition. And on every cycle, we can take the result of that smoothing, feed that back out, and use that in another calculation to solve where we want our desired position to be. And that's the way we have to do this. So that's where it starts to get a little dicey. So what I want to do is just kind of break this down. I like blocking things. So we're going to, well, hang on. Let me not just write smooth. Let's say calculate distance smoothing. Now everything you see here is going to be happening on every cycle. Okay, we're going to calculate our distance smoothing. We need our distance smoothing along with our, isn't it our mouse X and our mouse Y?
Yes.
So we're going to take, well, actually, that's where our desired position is going to come from, really.
Right.
We're going to take mouse X, comma, mouse Y, comma, and whatever our distance happens to be right now, understanding full well that our distance is probably changing because of that smooth calculation. But remember, all this is happening on every update. So where's distance right now? It's just because it's happening to move along a smooth curve like you see here doesn't really mean anything. Not at the moment. So now we're going to take our mouse X, our mouse Y, and our mouse distance, and we're going to calculate
a position based off of that.
What position? The desired position. That's pretty easy to understand. It's just, it can get tricky to think about because we're going to be handling the smoothing of distance here in calculate desired position. But we're going to be handling the smoothing of our position in update position later on.
Right.
But that's, again, that's because we have to have distance finalized or we can't get anywhere.
Right.
Don't worry, though. We're not done making it interesting just yet. This step right here, defined by these two blocks, where we take our mouse X, our mouse Y, and our distance and calculate our desired position, this is actually going to be handled. I thought about doing this on a new piece of paper, but I won't. This is actually going to be handled in its own method. This is where it starts to get funny. We're going to create a method simply called calculate position. It's generic.
Right.
The description for it is generic because it's just calculating the position. It just so happens we are going to use it in the calculate desired position method. We're going to call calculate position to help us calculate the desired position. But the way you can look at it is that calculate desired position is going to do two things. It's going to fire off the smoothing of distance. In fact, hang on. Now I need my new piece of paper. I was about to, but now is a good time as any. So do I have anything on this sheet? No. Excellent. So let's come back over here, make sure I'm on the right layer, otherwise I can't draw anything. Yes, Photoshop. Thank you very much. Okay. So let's just talk about the calculate desired position method now. Awesome. It's really only going to do two things. The first thing it's going to do is process the smoothing for distance. And it can, because we already have that desired distance. We have our current distance. All we have to do now is run a very particular function. And we'll talk about that and how it works here in just a moment. And we can get the result of our smoothing. Next, we're going to call on a new method, calculate position. Calculate position is the real workhorse here. Calculate position is it's something that we could call from anywhere if we really wanted to. We'd have to make it public. But what we're going to do is basically offload the mathematic equations over to a brand new method, which again we're going to call calculate position. So let's just talk about that. We'll draw a whole nother box here. And let's just talk about what calculate position is going to do. Now, calculate position is a little bit on the fancy side. It's going to take in some stuff and it's going to return some stuff. First off, we need to know its return type. What's it going to return?
We're going to return a vector 3. In other words, we're returning a position.
We'll write that down. Just like that. We'll say we'll return a vector 3 in parentheses. That'll be our position. What position? The desired position. But that's not important. You could use this to calculate any position you liked. It just so happens that we're going to use it to calculate the desired position.
Right.
I just want to make sure that that's understood. Because we don't necessarily need to calculate the position of the camera. We already have that.
Right.
So if you're thinking calculate position is trying to figure out where we are, no. It's a generic method whose job is going to be used. It's going to be to help us figure out where the desired position is going to be.
Right.
All right. So it's going to return a vector 3, which we'll use as position. It's going to take in some stuff too. It is going to be taking in what exactly?
It's going to take in a rotation x, which is the rotation around our target look at. Around
Like the orbital ring?
The orbital ring around the x-axis.
Okay.
So this would be the up and down.
Yeah, that's what I thought. So, and I'll talk about that here in just a second. As a matter of fact, okay, no, hang on. Let's just one thing at a time here.
And the next is rotation y. And this is the horizontal rotation around our target look at.
Right.
Then it takes in our distance. That's going to be the distance or how big this orbiting sphere ring is from our target look at.
Which comes back to why we have to process smoothing for distance first. We need the result of that so that we can feed it into our calculate position method. Now, this is where things get a little bit on the interesting side because we're going to flip a couple of axes here. Now, and before you get too scared, if you think about this, it makes perfect sense. Because now we've got to change coordinate systems. We've got to change from what makes sense on a mouse, and forgive me, I'm going to draw another mouse here. So that's a really, goofy mouse, and then here's his little cable, so we know he's got one. Mouse has two axes, as we already determined. He's got the X horizontal axis, and he has the Y vertical axis. And really, it's side to side and forward and back, technically speaking. But when we're rotating an object in 3D space, it doesn't exactly work that way.
No.
So, and technically what we're rotating is our camera. So we'll just go from that. So we'll draw out a camera. Now this camera exists in 3D space. So if it's going to rotate on its side-to-side axis, that is going to move it up and down. Because remember, you rotate about an axis. You don't slide along it or anything like that when you're rotating. And its side-to-side axis is X. So the vertical motion, the forward and backward motion on the mouse, is going to be associated to the camera's X-axis.
Even though it is the mouse Y,
Right.
it's the mouse Y value is actually the rotation in X for our camera.
Well, and here's another way to look at it. Mouse Y equals up and down, which equals rotation along X. Up and down is handled via our X rotation. So that's how you make the transition. Mouse X, on the other hand, is side to side, which is actually handled via our Y rotation, which is the up and down axis running right through the center of the camera. So, literally, Y becomes X, and X becomes Y. That will give you a headache if you don't stop and think about it. Hopefully you're watching it right now going, well, that's no big deal. Of course it's that way, because you want the vertical, the forward and back axis when you're moving the mouse up and you're moving the mouse back toward you. You want that to control the elevation of the camera. So you've got to spin the camera on its local side-to-side axis, just like turning a knob. Then, for rotating around our orbit, we've got to rotate around an axis that runs vertically through the center of the camera, and that's Y. So that's how we flip things over.
But it's not just as simple as that. It's even a little bit more complicated.
But not too much
Right.
more complicated.
Because
honestly, I think if you made it that far, you're home free. You're done.
Well, the trick is you got to remember our pivot point isn't actually the center of the camera. The pivot point is our target look at.
Right.
So we're still rotating around the same axis.
Right. Now, I was just bringing the camera in as an example. But again, if you really wanted to be technical, the center point of all of these axes would have just been a little crosshair that means nothing, and that would be our target look at. So nobody can get on to me for not being technical about it, but wow, the camera was a whole lot more interesting to look at in that diagram.
It was. I'll give you that.
All right, so let's see. Now, we're going to be feeding this in. Now, it's important to know this flip, because when we actually write this out, when we call on calculate position, the way we're going to do it is calculate position. Now, look at what it's expecting. It's expecting rotate X, and then it's expecting rotate Y. So we're going to feed it mouse Y to drive rotate X. Then we're going to feed it mouse X to drive rotate Y for all the reasons I just discussed. And then we'll feed it distance, like so. That is how we're going to that's how we're going to call it. Now again, honestly, I think if you made it that far, you're home free. So what's the difficult part?
Well, after we've done that, we have to actually do a little bit of math to figure out the orbit of the camera. And because if we were to just do this and apply it to our camera, we would be rotating our camera correctly if it was a first-person camera.
Sure.
But because this is a third-person camera,
There's got to be an offset.
There's offsets. So what we end up doing next is we have to create a new vector that we call direction. And this direction is going to be based off of our distance. And in an initial state, we know that our distance should be behind our player or our character.
Right.
So what we need to do is create a vector in such a way where the x and y is 0, but the z-axis of that vector is the negative of our distance.
Okay.
That will move our camera the distance away behind our player.
That makes sense. Now, again, that's just for starting purposes. Yeah?
Right.
Yeah.
The next thing is we actually have to build our quaternion, which holds our rotation.
Yeah, but we're going to be building it from Euler rotations anyway.
Yes.
Yeah. So, okay. So that's not too bad.
No,
yet.
no.
So, 2, we're going to build a new quaternion, which, what are we going to call that?
We're going to call it rotation.
Ah, yeah, you with the names.
Yep.
Which we're going to call rotation. Now, how are we going to assemble that?
Well, it'll be basically using a quaternion, calling its Euler, and then sending in rotation X for X, rotation Y for Y, and for the Z, we're going to send in 0 because we have no roll.
Yeah, we're not rolling the camera. And these would be the rotation X and the rotation Y that just got passed in.
Mm-hmm. And then the magic happens in the third step.
All right. Step 3.
Step 3 is to return our position that we're going to calculate. Our position has an origin or a pivot point. That is going to be the position of our target look at.
So basically, we're starting off wherever the target happens to be.
Right.
Okay. So we're going to return target look at
Dot position. So we're going to start at our target's position. Then we're going to add a new vector to it.
Okay.
That vector is going to be created by taking our rotation and multiplying it by our direction.
Okay, which is why we had to solve for direction a moment ago, and we solved this new quaternion called rotation, and that will offset our vector by exactly where the camera needs to be relative to the target.
Right. That calculates our whole orbit around, and technically if we didn't have the target look at position, that would rotate our camera around 0. And then we're adding our look at to offset.
So by calculating all this stuff, and I almost really do need a new sheet of paper here, but I don't want to lose this stuff that I've got. So what I'm going to do instead, will you hit Control A for me? Actually, let's just bring the keyboard over here. Let me do something a little bit fancy.
There you go.
We're going to, let me see here, just change my mind. Let's just slide this up. I can get back to it in just a moment if I need to. So, what have we done here? Well, we've started off by creating a new vector called direction, which is just the negative of our distance. So really, it would just be a vector that is 0, 0, negative distance, yeah?
Yes.
Then we make another vector, essentially. Well, it's a quaternion.
Right.
Right.
It's a little bit different.
Right. Which, now, how would that actually look if we were to write it out? It's taking the
quaternion.
Well,
it's actually a matrix, so we don't want to be drawing it out.
We're not going to go that far, but it's starting off with whatever our rotate X was and our rotate Y. And those were fed in from mouse Y and mouse X. So if you wanted to get really technical, it would be mouse Y, mouse X, then 0, and then this would be converted over to a quaternion. Then we're going to multiply this times this. So let's see. Let's just make sure I'm getting this right. So this is rotation. No, this is direction. Thank you.
Right.
This is direction. This is rotation.
Right. And if you multiply a vector by a quaternion, you get a vector back.
That's right. And the vector we would end up getting is going, well, I'm not sure exactly what the numbers would be.
Well, right, because that's the magic of the quaternion.
That's the magic of it.
What it's going to return is going to be some point in space around the origin offset by distance.
Right.
Or our negative distance.
That's right. And then because we're adding that to our position,
then we're offsetting that whole thing because we're doing vector addition at that point.
Right. So we're starting off at 0, 0, 0. And then we would literally be defining a distance and elevation around our orbital axis that we had. And then to that, we add the height of our player, or actually the location of our player, as it may be. And now we're suddenly snapped up to the top of the player,
which pushes our camera
up into the air.
Higher up into the air.
So now we're back up here, rotating back around like we should be. All that is handled within calculate position.
Right.
So that, and that's the great thing, again, calculate position is the real workhorse here. And all of his efforts are to return a final position somewhere along our ring, offset by our look at target position, so that calculate desired position gets that value.
Right. And it does. The nice thing about the calculate position equation is it's not only for desired position. The way it's broke out, we can use it later in our more enhanced versions to calculate some other things. You could actually use this equation if you had something that you wanted to orbit around another object, and then you could just send in a steadily increasing rotation x or a steadily rotating y, and it will take anything and orbit it around something else.
Now that is a really, I think it's a great breakdown of everything that we've got to do, but we never really got a chance to talk about the things that we needed to get this done.
Right.
So what do we need in order to get this done?
Well, we're going to need a distance smooth. So we basically need a public field that's going to be a float that we're going to use and call distance smooth. Now what this field is holding is the time that we're going to be smoothing from our current distance to our desired.
That's true, and I've got to actually talk a little bit more about how that smoothing is going to go.
Right.
Which we can now, because the hard part I wanted you to understand was how we're offloading the hardcore calculation of our desired position onto a whole nother method that we're just calling calculate position. And I know it sounds like a who's on first routine, but it's like all it's doing is calculating a position. What position? The desired position. That's how it's being named. It's not calculating where we currently are. We already know that. All right, so we're going to have a public distance smooth, and this is going to be a time over which we're going to smoothly transition from our current distance to our desired. I'm sorry. Yeah,
yes.
Our current distance to our desired distance. That's right. So this is transition time. That's all this is. Transition time. And we'll in seconds. Isn't it in seconds? I believe it is.
Yes.
In seconds. To move from current distance, or technically it's just distance. So I won't even say current because I don't want to confuse people. So from distance, which is where we are, to desired distance.
Right.
And I'm out of space, so we'll just abbreviate this. All right, now, of course, that's probably not all we need.
No, we actually have to keep track of a private field.
But hang on. Before we get away from it, I want to go ahead and talk about smoothing, and then we can talk about the other fields that we're going to need in just a moment.
Okay.
Because it's good that we already covered that we're going to need this, because now I can talk about smoothing with all of our ingredients.
So we need one more field to do that.
That's true. We need to actually store that velocity distance. Yep. All right. Now, that's going to be private, isn't it?
Yes. That's a private float. That's our velocity distance.
And you had abbreviated that to vel distance.
Yes.
You're like so verbose with everything else.
Until I get to my field.
Yeah, it's like you've got some methods that have chapters in their title. but we get vel distance. That's fine. No worries. I'm not complaining. And really, this is not going to be set to anything. This is going, well, not by us.
Right.
This is going to store... here's how I'm going to say this. Now, technically it's storing velocity, but what we're going to do is say this is going to store our point along the smoothing curve.
Right. And because it's saving a velocity, it's calculating the point along the curve and the rate of change of our curve. It's
right. Right.
Definitely
it is true. It is definitely a velocity, which is a rate of change over time. But again, it's moving along that curve, and it's constantly updating that.
Right.
We need that, though. Okay, now at this point, we really do have all the ingredients we need, so let's talk a little bit about smoothing. Now, a moment ago, I told you that smoothing is something that can easily be graphed out as a change in distance over time, where you have your start position. You have actually I shouldn't write it there because that's right in my way. that's so me. We've got let me try to put it down here. We have our start position, and we have our desired position. You could also call it target position or end goal, or there's all kinds of. But we're going to stick with desired position, and the motion is graphed out like so. You get an S-curve, a smooth transition, ease in and ease out. We accelerate and then we decelerate. So it looks all nice and clean and smooth, and you don't notice any jerkiness whatsoever. In order to do this, you need a few things. The start position is obvious. We need that. The desired position And actually, technically, these are all for distance, if we want to do it that way. So we have start distance in this case. The calculation will be the same for position, by the way. So, I mean, I'll be referring back to this when we get to that, so I don't have to draw all these graphs out a second time. But we can stick with distance for now, because that's what we're actually calculating. So we have our start distance, our desired distance. What else do we need, though?
Well, we need to know how long do you want to smooth between those 2 points.
That's right. We need to know how long this is going to take over. How long is the duration? And that is going to be defined by our distance smooth. So if we said that this was going to take place over 1 second, our curve would probably look something like this. I mean, it could look something like that. If we said it was going to take place over 3 seconds in the same space, or same kind of graphic space, it would be 3 times as long, and suddenly our curve would have to do this. So it's literally stretching out the time over which that curve exists. That's what you need to know. Now, on each update, each time this cycles, because this is not something that can take place instantaneously, obviously. This has got to take place over time. If our distance smooth, for instance, was set to 3 seconds, that means we've got to go from our start distance to our desired distance over the course of 3 seconds. But during that 3 seconds, we have all kinds of computer updates that are taking place, hundreds if not thousands of them. So what we're going to be doing is storing our velocity along each point of the curve inside velocity distance during each update.
And that's going to keep track of where along the curve we are.
Right. So all of this stuff, and put little tiny asterisks at each of these. This is all getting stored inside velocity distance. Right. So velocity distance will keep on updating. Now here's the deal. The way we're going to be doing this is we're going to say distance is equal to... Now, how does this actually go? How's the syntax go?
It's math F, so we're calling the math F class. And we're going to use the smooth damp.
Is that a capital F? I can never remember.
No, it's capital M, small f.
Okay, I knew it was something like that.
Well, that's what IntelliSense is for. You don't really have that with a pen.
All right, math F dot...
Smooth damp.
Smooth damp.
Now into it, we need to pass in our start, which is going to be distance. And then our goal, which is desired distance. We need to send in a reference to velocity distance, so that's REF.
That's true. Let me make sure I'm trying to stay. I'm running out of space. So vel dist, I'm going to abbreviate that. Sorry, guys. And then...
our distance smooth.
So dist smooth, and I have no room left.
Right.
We have to feed all 4 of those things in.
Right.
Now here's the deal. We're setting that back to distance on each cycle.
Which causes a complication with our smooth. You're not going to really notice it unless you start sending out extended smooth times.
Right.
Because what's happening is on every update, we're updating our start point. So our start point is moving along with our desired position.
So really, instead of sliding along this curve, we're basically constantly updating the curve on
we're
every
compressing
single thing.
the curve as well.
Yeah. Now, it's not going to cause that big of a deal, but it does mean we're not getting perfect smoothing from our result. The trick, though, is we have to do this because we need our distance calculation so that we can calculate our desired position later on. And we mentioned this earlier. The calculate position method relies on distance to be ready for us to go. So we've got to pull out wherever you are. We just got to say, all right, come on, let's go. And then we're going to base our calculation from that. Then when we come back, we're going to do this whole smooth calculation over again. Now, the result will still look smooth. So keep that in mind. It's not like we're necessarily ruining this or anything.
Right, but if you're sitting there with a stopwatch and going, I set 3 seconds and that was not 3 seconds, this is why.
Yeah, there's going to be a little bit of a variable in the timing, and that's why. So that handles smoothing. Now, I realize that was a little bit of a segue because I just wanted to go into what we need, but once we got to the point where we had added in all of our necessary ingredients for smoothing, I did want to make sure and explain how that smooth damp was going to work under the hood. Now that we have that, I'm sure there are probably one or two other things we still need, like in the way that I need a new sheet of paper to continue.
Actually, for this method, those are the only two I need.
Are we really done?
Yeah.
Okay. And then we've already covered all the work for it.
Mm-hmm.
I mean, goodness knows I don't want to write all that out again.
Well, the fun part is when I actually sit down and code this for you guys, it's not going to look anywhere near as complicated as this theory is.
No, it actually isn't. But there are some subtleties that can throw you off if you're not staying on top of them. Things like how we're flipping mouse Y and actually sending that into rotate X, and taking mouse X and sending that into rotate Y. If you're just kind of idly going along, riding your little tricycle, your big wheel down the road, you're like, yeah, this is awesome, having a great time, you're going to hear the record scratch.
Right.
But, what's happening? Why are we flipping these over?
Oh, especially if you miss the inversion of the distance when you're calculating your direction, you're going to be sitting there, why am I looking at the front of my character?
Exactly. There's all these little tiny things. And then just dropping in mathf.smooth_damp and telling you to plug these values in is great, but it's so much nicer when you actually understand the calculation that's taking place because of that.
Right, because then you'll sit there and go, oh, geez, I've been using lerp forever.
And you don't have to.
Which is linear interpretation. We don't get the ease in and ease out that we get with smooth.
That's right. That's right. So again, we covered everything that we need to do, and I'm not going to go back over that again. There's just been so much of it. But our whole idea, just in really, really basic form, is that we've got to get that desired position. To help make this happen, we're going to create another method called calculate position, who's going to do all the work for us, really. And so we're going to have to process smoothing for our distance. On each cycle, we're going to have to say, hey, wherever you are, go ahead and give me your current distance right now, because I've got to hand that over to calculate position so we can figure out where we're supposed to be.
Right. And the other thing is, if you didn't really understand the discussion on the smooth damp and how that's working, listen to it again, because we are going to use it again in a couple of videos from now. So you really need to have a decent grasp of what's going on.
I don't think it's that bad. You just have to know what a smooth curve is, that it is an S curve. You're going to need to know that it requires where you are. It requires where you want to be. As a matter of fact, since you got me talking about it, and I just jumped back over to Unity, which I didn't mean to do.
Well, I haven't seen that in about 5 or 6 videos.
Yeah, I know. It's been a little while, hasn't it? So again, all you really need to know is that you need to know the ingredients. And that is that we must have a start distance. We must have a desired distance. We need a time over which the smooth calculation can take place, so we know the length of the curve, really. And then we're going to have to establish some sort of velocity factor that can constantly be fed out. That's just part of the math. Mathf.smooth_damp requires that.
Yep.
And once we know that, we're good to go. So, and then really, aside from that, it's just knowing that when you say the word smooth, you mean an S curve. That's just how it works.
Right.
So, again, I think we've covered everything about as far as we can. At this point now, it's just going to be coding it and let the results speak for themselves.
Yeah, the anticlimactic part of coding is like, oh, well, that's going to be like 1,000 lines of code. That's it.
But isn't that always how it works? Like, the smaller your code, generally, the more complex your program is. Anyway, so that is going to wrap things up for this video. Thank you very much for watching.